And thanks everyone for joining in today and giving me the opportunity to talk a little bit about causal inference today and kind of my thoughts and thinking on it. But since I think a lot of you don't know who I am, just a brief background. I received my PhD in 2018 in psychological science, specifically in quantitative psych from the University of California, Merced. So a lot of my training there was in Bayesian longitudinal analyses. But I had the fortune of having most of my grad program um, being there with Will Shadish. So a lot of the way that I talk about and think about causal inference is really influenced by classes and discussions I've had with him, and then the Shadish, Cook, and Campbell threats to validity. So yeah, just wanted to give everyone an idea of who I am a little bit. And now I'm an assistant research professor in the Center for Healthy Aging and in charge of doing a lot of statistical analyses for different kinds of longitudinal models. And we'll get started. So yeah, most of this talk will be about causal inference for just in general, experimental and quasi-experimental designs, but a lot of these principles are going to go over into other kinds of observational research. It's really about how to know if we have any causal relations in our data. And just briefly, I'll show this again at the end of the presentation, but my contact information, anyone that wants to email me afterwards to just chat, I love to just, sit and talk about stats and causal inference or research, anything really. If you want to talk about X-Files or skateboarding, I'm here as well. And you can find me in my office in the Biobehavioral Health building. I'm there often with my door open, welcoming people inside. Okay, so this is just a kind of a brief outline of what I plan to go over today. So I'm going to start off talking about what causal inference is, and talk about correlation and confounders. And then once we kind of understand what causal inference is, cause and effect, the next part is going into like, how do I know if I have a causal relation in my data? Does the type of data that I have lend itself to being able to do that? How can I design studies or new studies to look at causal inference? And how can I look at studies that already exist and seeing if there's a way that we can kind of gain some more causal evidence? And that'll be more in the third part, the directed acyclic graphs or DAGs. And just some, much of this talk is kind of drawn from the Shadish, Cook, and Campbell 2002 Experimental and Quasi-Experimental Designs for Generalized Causal Inference book. That was one that I used in grad school, and I still come back to it many times just to help me understand and help me understand what's going on with the data. And there's also a newer book out called Causal Inference, the Mixtape by Scott Cunningham, and I think he came and gave a talk last year, just kind of based on his book. But he has a really nice description of DAGs in here, among other methods. The interesting thing is the Shadish, Cook, and Campbell book is very like statistics free. And the causal inference mixtape has a little bit more focus on DAGs and then statistical methods as well. So the way I kind of think about causation and cause and effect is it's more about the design of the study and kind of the validity of inferences that we can make. So how can we make the causal inference? So I think you'll see throughout that I think of it as more of a qualitative judgment. There are a lot of statistical methods developed to assist us with cause and effect, but without a really solid study design, understanding of theory, measurement of variables, those statistical methods that are developed are going to be limited due to the design of the study. So much of this talk is going to focus on how we know if there's a causal effect and are present, and how can we design our studies more effectively to target these. And one of the takeaways of this is going to be that I hope everyone, as they design studies, considers different factors for cause and effect, even if ultimately they don't look at a causal relation in any particular paper. All right, so causal inference is a central goal across all scientific disciplines. It's needed for developing interventions. So how do we know that a certain treatment's going to impact an outcome of interest? Maybe it's a therapy intervention to help reduce depression. How do we know that therapy intervention actually reduced depression? Causal inference can help us with that. Identifying risk factors for different illnesses or atypical development in aging. So a lot of my work kind of been back and forth between child maltreatment and aging research. So how do we know that children who are maltreated are at risk for different kinds of developmental and aging impairments or harm to their well-being and health throughout their lifespan? Even when we're doing work, doing our research, and we're not thinking in a specific study that we can do causal inference, often our research questions are causal in nature. So, I've done some more psychological-based studies where I was interested in whether being optimistic in a moment was related to blood pressure and if it affected stress reactivity. The specific design of the study I had didn't really lend itself to causal inference, so it was more of a correlational associational study. However, the question was still causal in nature. My research question, the theory that I developed it through, all pointed to optimism and pessimism leading to some kind of outcome, although it's totally possible that some of the outcomes under study could also affect optimism and pessimism. And one of my goals here is to kind of help us not stop at just correlation, but think, is there anything that we can have, maybe in data that's already collected? Is there anything in there that can provide a little bit more evidence towards a potential causal association? And you see this in a lot of papers where the language can get a little fluffier when you could tell the author wants to talk about a causal relation, but they try to rein themselves in and use more roundabout language because it's not causal, it's a little bit safer. You're not going to get a criticism that you're talking about an effect when we really don't know directionality. But sometimes in our data sets, there's some variables that can help us provide some kind of evidence. So to understand causal inference, there's a lot of terms that have to be defined. And a lot of these terms have been argued about by philosophers for hundreds of years. And more recently, with experimental design becoming more prominent in science, so in like the 1800s and later, the terms have started to get a little bit more clear. However, a lot of these terms are kind of dependent. The definition of one is dependent upon the definition of the other. So often you'll see something like something that produces a simple or complex idea is a cause, and that which is produced is an effect. And that's like a definition to understand cause and effect, but they're kind of using each other. And that's not a great definition to have. It's not clear, then we can't look at it in and of itself. But a cause is, it could be it's something that you do, and an effect is the result of what you did. So you may think if another car hits your car, it's the cause of the damage. The damage in your car is the effect. That other person's car hitting you is the cause of the damage that you received. So sometimes just metaphors or just examples kind of help us understand these terms a little bit better. So one of the difficult parts in identifying cause and effect relationships in the behavioral, psychosocial, biomedical fields is kind of understanding this overall treatment package. So we have a manipulation and we see a difference in outcome. from some group that received the treatment and some group that received some control, or a group that didn't receive any treatment. But that intervention that we provided people is usually more than just one thing. There's a number of conditions that are part of that. It's like an entire treatment package. And sometimes we can make a control group that has everything but that one component, but that's can be very difficult. So most of the causes that we look at in just science in general are what's called Enos conditions. So an Enos condition is something that's insufficient but non-redundant, and it's part of an unnecessary but sufficient condition. Again, that's very like philosopher kind of talk. So I'm going to provide a very concrete example, a couple different concrete examples, and I have these are straight from the Shadish, Cook, and Campbell book, but one thing we can think of is using a match to start a fire. So a match can be a cause of a fire, but it's only one way to start a fire. So for instance, I'm from California, so I know all the ways that fires are caused. So like lightning strike, for instance, or someone throwing out a cigarette on a side of a dry highway. So there are multiple things that can cause a fire. So a match is not just the only cause. And there are a lot of other conditions that have to be met for a fire to occur, right? We can't just have the match in and of itself causing a fire somewhere. There needs to be something to fuel the fire. So oxygen, for instance. There needs to be some kind of kindling or something for the fire to burn, so dry leaves. So a match that you hold to a rock is probably not going to cause a fire, but a match that you hold up to a large pile of dry leaves may cause a fire. So we see that a match is actually what's called an Enos condition because in and of itself, it's just being there is not something that's going to necessarily cause a fire unless other conditions are met. And if we see that a fire has occurred, it doesn't mean a match caused it. But there are also some real life examples of this Enos condition. There's a famous one in the biomedical sciences from Folkman in 1996. So he found a new drug that shrank tumors, and it did this by restricting blood flow to them. Like, that's incredible finding. However, other scientists kept trying to replicate the findings, and they would have the exact same materials sent from the Folkman lab to them, and people were not able to get the same results. So, there's obviously a lot of debate going on about this, and these scientists who wanted to replicate it then decided to travel to Folkman's lab. And what they did there was just learn what the exact protocol was that Folkman did. So let's see him do it, and let's ourselves go out and do it using the exact same methods. So they learned how it was manufactured, the drug was manufactured, transported, the conditions that it was stored under, so like the right temperature that it was stored, how it was handled, and importantly, how the drug was administered. So what angle was the needle when they um, um, injected the drug. And once this happened, once these scientists went to his lab and learned how to do the entire protocol exactly the way it was, they were able to replicate the findings. The tumor shrinkage was happening, the blood flow was being restricted to the tumors. However, nobody knew exactly which details of that protocol were important. So it wasn't just injecting the medication or the drug in that did it. It was something about the entire package. But the injection of the drug was crucial. That needed to happen, but it needed to happen with some other components of that entire protocol. And it wasn't clear which ones, but it was clear that if you did it in this particular way, that the drug was effective. So that meant that that drug was actually an Enos condition. I've actually never said that acronym out loud, so I'm going with Enos, but if other people have a different way, let me know. Okay. So Actually, one more thing about this Enos conditions, then this kind of means that a lot of the causal associations that we look at in just science in general, they're not deterministic, right? So deterministic means that if A causes B, then every time A happens, we should see B. They're actually probabilistic because there's so many other factors that are considered as part of these packages. So probabilistic here would just mean that if A happens, B is more likely to happen. And that kind of fits better in with the Enos condition because we see with this drug, just injecting the drug didn't cause the tumor to shrink. Injecting the drug increases the likelihood of the tumors to shrink um, with all these other factors together. Okay, so that kind of gives us a better idea of what a cause is. So the cause is something that we do, something that we ideally manipulate ourselves, but it could be manipulated in other ways, like naturally occurring, um, looking at differences in gender. But an effect, I think, can be best understood by thinking of a counterfactual model. So counterfactual model is kind of an older idea in causal inference, but it's really about something that's contrary to the fact. So a factual is what we know, a counterfactual is something that we don't necessarily know. So when we do, like, say, a randomized experiment, we observe what actually happened. So we put people into one group of people into therapy, and we put another group of people into like a waitlist control group. So maybe they'll get therapy later, but during this time, they're just, going through life as they normally would. So what we actually know is that what the people's outcomes are for the conditions that they're in. The counterfactual, though, is the knowledge of what would have happened to those same people had they been in a different condition. So the people who received the intervention, what would they have been had they not been in the intervention? What would their outcome have been? Likewise, the people in the control group, what would their outcome have been had they actually been in the intervention instead? So the effect in a cause and effect relationship is actually the difference between what actually happened and what would have happened. So this is another issue you might be able to see is, do we ever actually know what would have happened? So counterfactuals, unfortunately, cannot be directly observed. So all researchers looking into causal inference, one of the main goals is to try to create some kind of reasonable approximation of the counterfactual. And there are a lot of different ways to go about this to provide us stronger evidence that we have a comparison group that is actually represents what the people who got the intervention would look like had they not. The important thing to note, though, is that it's when we try to create a counterfactual, so like a control group, some group that we can compare people to. We try to make them as high quality as possible. So we try to make them as equal as we can on everything. But say we're doing like human subjects research, for instance, it's still different people in each group. And ideally, those things kind of will wash out and not matter, but they're different people. So the counterfactuals that we create, the goal is to make them as high quality as possible, but know that they have to be imperfect by nature. And so we also have to then know that that source of imperfection, how it differs from the actual treatment and exposure condition. So one of my dissertation study, I spent a lot of time thinking about counterfactuals and specifically how to make a control group. So I did an experimental design where I looked at people who took the Trier social stress test, which is a laboratory-based psychosocial stressor where people have to, give a pretend job talk about their dream job to a panel of experts, specifically nonverbal communication. So that this group of undergrad RAs would sit there wearing lab coats and writing on notepads and looking a little bit annoyed. And it's kind of unnerving. A lot of people have trouble doing that. Even people that know the purpose of the study show a very strong stress reaction often. Um, but what I wanted to see there was whether having stress affected the way that people processed information. Did they look at the world as a more abstract or concrete perspective, which has all sorts of implications for how you can receive an intervention, um, how you make judgments and decisions in your daily life, for instance. So in order to make the control group, I needed to make everything to be as much the same as possible. Um, and I started thinking more that like just having people sit in the room or write about their job, those differences may actually impact whether they how they're processing information. Because if you're speaking to a group of people that you don't know versus if you're just writing down information, um, even if it's a non-stressful situation, that may put you in a different mindset. So there was a lot of work that had to be put in to making those conditions as equal as possible. However, there's still strong differences. Like I ended up having to make everybody stand up the whole time in the same location, but the people in the control group were still writing about an experience that was in a room with nobody else in front of them. So there are still, it's not a perfect counterfactual, but there was a lot of effort put into it to make it as high quality as possible. So that leads us to the term causal inference. So causal inference, once we have our cause and our effect established, it's just the ability to say that it's these two variables that we found to covary, so they're related to each other. That relationship is causal. So we think one variable changes one variable lead to changes in the other variable. And yeah, so that's the whole goal of what we're doing here is how do we make these two variables that are related? How do we determine whether it's a causal relation or something else? So one of the common things that you tend to hear in causal inference work is that correlation does not prove causation. I hear that a lot, and that's often something that I hear to discredit a lot of different research designs. If any of you have submitted a paper and have accidentally used a phrase that was tangentially related to causation, a reviewer may have said causation doesn't prove correlation, but it it does need it's helpful if there is a correlation present for covariation or causation, but it doesn't mean that there isn't a cause. It just means that we need to think more deeper to figure out if we can um, provide evidence for that causal relationship. The interesting thing, though, with correlations is there's a lot of reasons that you may observe a correlation or may not observe a correlation. So correlations can be spurious, just two things happen to be related by chance. There's no actual real reason that these two variables theoretically would go together. And those are the kind of instances where we might just say like, oh, that's just random chance. That can happen. We all set our alpha levels to 0.05, so we're given that 5% type 1 error, or whatever alpha level you use. Correlations don't tell you the directionality of the association. So if you just have two measures measured at the same time, you don't know why they're related to each other. If one's causing the other, if they cause each other in a complicated relationship over time. And also, they can't rule out something that's called a confound. And I'll talk more about what confounds are later, but it's basically just a another variable that explains the relationship. And another interesting thing that happens with correlations, though, is sometimes you observe no correlation between two variables, and that does not mean that there isn't a causal relationship among them. Um, so a lot of the work I do is with ecological momentary assessment. So that's individuals get um, we measure them multiple times in their daily life for multiple days. So maybe 5 times a day for 2 weeks. So we have a lot of these assessments within individuals, and we do the statistical analyses. We have to figure out how to separate um, differences between people from differences within individuals. We go through this process where we create variables that represent only between person differences and another one that represents only within person differences. And often the approach that we take leads to two variables that are not correlated with each other at all. It will be a zero correlation, but they are deterministically created or related because they are created from one another. Um, an example that was in the Shadish Cook and Campbell book um, was about someone steering a boat in choppy waters and during a storm. So they're turning the rudder and the boat keeps going straight no matter which direction they're turning the rudder. They turn it to the left, they keep going straight. So you might look at that just by measuring direction they're turning the rudder and the direction the boat goes and say there's no correlation between those. It's zero. They go straight no matter what. However, other factors are affecting what's going on with that relationship. If you were to randomly assign people in that same condition to just, flip a coin, heads go to the left, tails go to the right, you're going to see the boat moving in all sorts of weird ways. It's because when they're turning the rudder, it's to overcompensate for the boat going a different direction due to the wind and the waves. So if you account for the correct factors, then you might actually see a relationship that's not there. This is why it also becomes very crucial to understand the literature that you're looking into, to understand what relationships would you expect and what conditions would you expect them to happen under. And are there other factors that may influence the relationships you're looking at or the relations you're looking at? Yeah, I guess now is when I was going to talk about confounds. This will also come up later on when I give a brief, overview of what DAGs are. And confounds is a big part of that, but it's a big part of causal inference in general. So a confound is a third variable or some additional variables that explain why you may see a relationship between two variables. So there's a lot of like just funny examples that you do see in real life. So the number of shark attacks is correlated with the ice cream sales. So why would that be? And if we look into it deeper, we may say like maybe that's just a random spurious relationship, or maybe there's some reason that those two variables should be related to each other, but not in the way that we think, not causally. So these two variables probably don't cause each other. Selling more ice cream isn't going to lead to more shark attacks. More shark attacks isn't going to cause people to buy ice cream. Um, However, temperature is a variable that affects both of these. So it's a potential confounder. So when temperatures are higher, people are more likely to buy ice cream. And when temperatures are higher, they're also more likely to be swimming. And if you live on the coast, maybe more likely to swim in an ocean that could potentially be inhabited by sharks. So as temperatures rise, you have more ice cream sales and you have higher shark attacks. So the reason those two things are related is through temperature. So if we wanted to look at how ice cream sales cause shark attacks or the other way around, we would need to control for temperature. And once we control for that, we would see that there's no relationship or relation among those two variables. This is also a similar kind of relation we see with crime rate and ice cream sales. Those are also correlated, and it turns out the similar thing with temperature. As temperatures increase, crime rate tends to go up and ice cream sales tend to go up. So this is a picture I like to kind of show the difference in correlation and causation. A researcher or a child or anyone may come by and see um, a seagull sitting on this steel pole, and maybe you think that from looking at this, maybe steel poles that are long are weaker than steel poles that are short, because clearly the seagull on the short pole, it didn't bend, but the seagull on the long pole, it did bend. Or maybe it has to do with the height of the poles. So lower poles tend to be weaker than higher poles. Or it could just be that that seagull happened to land on that inflection point there because that's a comfortable spot for it to go to. And it happened to get there before the other seagull. So sometimes when we just observe a relation between variables, it doesn't mean there is an actual meaningful relation. There's other factors we need to consider that will help us then see that the relation we're seeing is due to something else. And one thing I like to show in courses, uh, I mean, when I just teach correlation in general, but also anything in causal inference, it's from this website by Tyler Vigen, and it's called Spurious Correlations. And the website is full of all sorts of different very funny examples of two variables that are actually very highly correlated in real life, but it's just because they happen to be related to one another by chance. There's no actual meaningful relation among these. So the one that I pulled here is the distance between Saturn and our moon. So because we have our orbits, the planets are always kind of changing distance from one another. That's directly correlated to the number of bachelor's degrees awarded in the physical sciences, just overall. And you can see these two lines overlap pretty highly, and the correlation is 0.987. So you remember correlations range from -1 to +1. So this is almost a perfect correlation between these two variables over time, but this is just because for the purpose of this website and to demonstrate spurious correlations, he just went out and looked, got the correlation of as many things as possible and found the ones that just didn't make any sense because, if we set our alpha level to 0.05 or 0.01, we're still saying that we're going to make a type 1 error that percent of the time. And in this instance, we could even find very strongly related variables that are still just by random chance. So it's another note. The strength of the relationship doesn't necessarily make it more real. It could still also happen just by chance. Okay, and I did mention this earlier, but an important distinction that we have to go over, and it's I think worth mentioning again, is that a deterministic cause is if A causes B, then B must always follow A. So you can think of on Earth, for instance, if I drop an apple, it's going to fall to the ground every time. The only time it won't is if I'm somewhere where gravity is different than here. It could fall slower or it may not fall, depending on where we are. However, what we deal with in the social, behavioral, biomedical sciences are what's called probabilistic causes. So A results in a higher probability of B. So, uh, this is really clear in psychology. There's a lot of individual difference in people, even when we do an experiment and we do a design where we can actually see how people have changed before and after. You'll see that there are some people that don't change. Even in studies that are more correlational and we're not actually trying to establish or make any causal claims. Say, for instance, we do a multi-level model and we allow we allow people to have different intercepts and different relations between the two variables. If you were to plot those, you would see, even in that instance, that some people have no relation between the variables. Some have a positive relation. Some may even have a negative relation. So there's a lot of heterogeneity in what we would see across individuals, but we do see that overall it tends to be um, when A happens, there's a higher probability of B. Not that every instance has to be that. Okay, so now I've just done a brief overview of what causal inference is and some of the terms, and kind of highlighted um, what correlations and confounds are, and spurious correlations. So it's kind of basic factors that are important to understand when trying to identify and evaluate whether something's causal relation. But I wanted to check at this point if anyone has questions or something they would like clarified there before I go on to these next topics, which I think get a little bit more complicated. Okay. Well, if anyone does have questions, feel free, again, just to unmute and interrupt, or shoot something in the chat, and um, someone will notify me of that. So this next part that I'm going to go into is how do you know if you have a causal relation between two variables? So we could say that we have identified that two variables are related to each other, but as we have talked about earlier, there's a lot of reasons that two different variables can be related to each other. So I'm going to talk first about statistical conclusion validity, and then I'm going to talk about internal validity. And then I'm going to talk about the different kinds of research designs that can be used to rule out threats to internal validity. And that phrase, threats to internal validity, is going to make more sense when I actually define what that means in the upcoming slides. And any of those that are familiar, this is very Shadish, Cook, and Campbell, like to a T right here. But I think this is kind of crucial to understand the components of this, which then become visually depicted when we look at the DAGs later on. Okay, so there's some conditions that have to be met for us to know that a causal relation has actually exists, or that for us to establish one. And John Stuart Mill, a long time ago, came up with these three conditions that need to occur for us to say that's one variable causes another variable. So the first is that the cause has to happen before the effect. So we can't have a situation where we see something happened and then later on what caused that thing to happen occurred. So this is what's called temporal asymmetry. So the two variables need to happen at different, or the cause and effect have to happen at different time points, and the cause always has to come before the effect. That's kind of the way time flows. So that's kind of where we're stuck right now. We also need to see that the cause is related to the effect. So the two variables need to be related. I know I mentioned earlier that with the boat example, that turning the rudder in that specific way, you might see a zero correlation. It doesn't mean it's not causal, but those are other variables that have to be measured in order to then be able to see that causal effect. So we need to be able to see that there is a covariation between the variables. And the most important one, and this is what's really going to drive um, the next parts of the slides that I go over, is that we can find no plausible alternative explanations for the effect other than the cause. And I want to highlight here the word plausible. So there will always be something that can possibly explain your results, but there may not be any evidence for it, and it may be unlikely to explain the associations that you have. So what's really crucial is that you find anything plausible. So something that there is evidence that there's evidence that these other factors could explain what you're seeing. And I'm going to go over kind of the different ways that we can do that, and you'll see what plausible means. And it's a good tool in argument and debate, and especially when you're discussing scientific finding, is there needs to be some evidence of the alternative explanation. That's what makes it plausible. If it's just that it can potentially happen, but there's no evidence that it did, it's not plausible and it isn't necessarily something that we need to put a whole lot of our effort into explaining away. So validity is um, kind of, it's a word that gets used in a lot of different things. But in general, we want to know if we can find truth in our inference, whether it's causal, whether it's statistical. There's other kinds of validity as well. So do we have evidence that the measure that we used actually measures what we think it did? Um, do we have evidence that the findings that we found in our sample generalize out to everybody? It's important to know, though, that validity is a property of inference. It's not really related to the design or the method. So this leads us to, randomized experiments are not inherently valid. They don't have inherently more validity. There's other factors that have to be considered in those kind of designs as well before we can make a valid inference to any of those areas. But really, we're just saying is what we think we're seeing real? It's is the inference that we're making about what we're seeing the truth? So if I think that something is a causal relation, how valid is that claim? So the different kinds of validity that are at least laid out in Shadish, Cook, and Campbell are external validity. So does the results I find generalize beyond the study? And that could be to different people, different places, different times, different instruments even that we use in the study. Construct validity. So that's really dealing with, did you measure what you think you measured? Um, in some fields, that's a lot less of a problem than others. So if we need to measure someone's height and we have a ruler or tape measure, that's, we're confident we're measuring how tall they are in inches or feet or meters. But if we're in a psychological science and we need to look at someone's depression, um, we have to do a lot of extra work to make sure the instrument we're using is measuring what we think it's measuring because there's not necessarily a direct way to measure that. The two, so in this talk, I'm not going to spend any more time on those two types of validity, but the two types that I will focus on are statistical conclusion validity and internal validity. Those two are crucial for us to actually make causal claims. So statistical conclusion validity is really boiling down to, did you use the correct statistics? The correct statistical method, and we'll go over the different ways that problems can arise from that. And the kind of crux of all this is internal validity. So is the causal claim real? And statistical conclusion validity kind of overlaps a little bit with internal validity, but internal validity is really where we get to understanding whether what we are observing is causal or not, or if we have evidence for it to be causal. Okay, so statistical conclusion validity concerns two related statistical inferences that affect the covariation of a causal inference. But in general, just even a statistical inference. So we need to know whether the two variables covary. So that's a statistical method that we have to use. And if it's cause, it's the cause and effect. If it's not causal, then it's just variable one and variable two. And we need to know how strongly they're related to each other. So that's the magnitude of the association. So if you're doing a correlation study, that's just your R. If you're doing a regression, there are different ways to conceptualize what the magnitude is. Sometimes it depends on the variables you're measuring. If there's a meaningful metric, it could just be, the actual raw estimate that you get. If it's not a meaningful metric, then you may have to do some type of approach to get a standardized estimate that gives us some kind of insight into how strong the relationship is in a scale that's more intuitive. Now, this is important because if we use the wrong statistical method, we could, make more type 1 or type 2 errors. So, for anyone that's not familiar, a type 1 error is basically when you say that there is a significant effect, even though it's not there. So you made a mistake in your claim. It doesn't mean that you necessarily did something wrong. It could just be that by chance, two variables were related to each other and they weren't supposed to be. So that would be a type 1 error. A type 2 error would be when you make a claim that there is no relation between two variables, but there actually should be one. There's many different reasons why these things can happen. Part of it is the statistical method that you use. Other parts of it are how you measured the variables. So, um, so yeah, not only can we make a type 1 or type 2 error, so make a claim about whether an effect exists or not incorrectly, we could also overestimate or underestimate the magnitude of the effects. So we may say that two variables are very strongly related to each other, when in fact they may only actually be weakly related to each other. Which this can be important because two variables can be statistically significantly related, but have a very small effect size. And in some contexts, a small effect size is really important and meaningful. In other contexts, though, a small effect size doesn't really result in like meaningful improvement on a health outcome. So putting effort into, designing an intervention based on a tiny effect size that may not result in helping a lot of people may waste resources and time. However, a small effect size can also lead to a large number of people being helped. So it's kind of context dependent. What's your research question? Which conventions in your field? How do you actually define what a large effect size is? For instance, sometimes 1% can actually be really big effect size, and other times it's very tiny, and you should ignore it even if it's significant. So if we use the wrong statistical methods, we may assume that something is a large effect when it's actually really small, or we may think something is a small effect and ignore it when it was actually meaningful and we should have put resources towards that research idea to develop it further and maybe do studies that lead to interventions that can help people. So this is a list of some of the threats to statistical conclusion validity. So these threats are anything that undermines our confidence that the statistical method that we use is actually getting us the correct, anything that undermines our confidence that the covariation we observed is real and that the magnitude that we observed is also real. So the next slides are going to go over each of these individually, but I wanted to have this slide up just, for me, when I'm going through this, I kind of, I pull up that page in the book and I have the table up that lists all those because for me, it's nice to have just like a checklist to go through. Yeah, so the first thing that we have to consider is low statistical power. And I think this is one that's a little bit more commonly known, especially those of us in the social and behavioral sciences, where what's it called, the replication crisis is talked about all the time, and whatever that means, but statistical power is often one thing cited. So statistical power is our ability to detect an effect that's real, an effect that actually exists. So we can assume that in real life, there's a relation between two variables. How often can we actually find that relation? And our ability to find the relation is a function of how many samples that we have. So depending on your design, it could be the number of individuals. It could be the number of time points per individual if you have a longitudinal design. All of those factors affect power. If you're doing a Bayesian analysis, then it's different. The approach that you take for, or I guess a corollary to power is, it's a different approach altogether, but So if we have low statistical power, that means we can't detect effects that are actually there. And that could be because we have too small of sample size. Um, but luckily, power can be increased in several ways. So there are some designs that we can do in our studies. So if we use matching, blocking, or stratifying, if the sample is large enough, um, these kind of approaches can increase power. But if we have small sample size and not a lot of people within each condition, that can actually reduce power further. So blocking, for instance, if we have a sample of men and women, and it turns out that men are very different from women, that's adding a lot of extra noise. And our ability to detect an association becomes more difficult because we have to find that signal in more noise than we would have had before. It's like finding a needle in a haystack, and we're just making the haystack bigger. But if we can look at men and women separately, or in the analysis put a predictor or a interaction term for gender, then we are now creating two groups that are more similar to each other within their groups, and that can actually make it easier for us to detect an effect. So that is a way that could potentially increase power. Another thing that we can do is, oh, sorry, my cat's saying hi. Um, we can measure and correct for different covariates. So I'll talk later on about covariates in that we should consider when we look at DAGs. But a more old school approach to covariates is how experiments were done, and using ANOVAs and ANCOVAs particularly, they would control for variables that were only related to the outcome. And those are what I call precision covariates. So the whole purpose of those is to clean up extraneous variance in the outcome that can actually help us detect an effect. The one way that I will use something like this is, again, in ecological momentary assessment, we'll have people wear a blood pressure cuff throughout their daily life. But if anyone's done work on blood pressure, we know that if you're standing and then sitting and eating and drinking, doing different kinds of behaviors can actually affect what your blood pressure is at the moment. So if we measure what people are doing, what people are eating and drinking, we can control for that. And I've seen multiple times where no relation can be detected. And when I add those control variables, all of a sudden it's really clear, like stress in the moment is related to blood pressure in the moment, but only when I control for those extraneous variables. And if I had a much larger sample size, I might have been able to detect the effect, but it may have also shrunk the effect size. Um, the most straightforward way is to have a larger sample size. So if you want more power, just get more data. However, that's not always feasible. We have limits on funding, especially in um, this economy. Um, so it's not always easier to get larger sample size. We could also ensure that we have the same amount of people in each group. So if we're looking at a depression treatment, so some kind of psychological intervention, if we have people, the same amount of people in the control as we have in the treatment condition, that can help us with power. If the difference, the ratio between sample sizes in the groups gets too large, like say over 2 to 1, that's when you can start seeing that same. So if we have 100 people, we have a certain amount of power if it's 50-50 in each group. But as soon as it becomes more of a 2 to 1 ratio, that the amount of power for 100 actually goes down. We could have improved measurement. So just having better items that don't have measurement error, because items that have some kind of error in them also make it harder to detect an effect. My favorite one that's I see recommended is just, get a bigger effect size. So make your treatment stronger and you'll have a larger effect size. It's a lot easier to find a big effect than it is to find a small effect. But that's also not always feasible. And sometimes we don't want to do that because it may be that the magnitude or the strength of the treatment that we need to be able to detect an effect is not one that we can actually feasibly administer or scale up to some kind of intervention. So at that point, it becomes like we know that at a very high dose it works, but that's not a dose that we can actually give people. Another thing we can do is use a within subjects design. So within subjects design, that'd be like repeated measures assessments. So repeating the same unit, measuring them multiple times, and then looking at a within person effect instead of a between person. So that's it's interesting there is if we have a between person design with say 100 people and 50 in each group, we could have the same 100 people and in their first time points, maybe the first 3 time points they're in the control condition and the second 3 time points they're in the intervention condition. It's still 100 people in both, but because we're looking at how they change over time, we actually have a lot higher power. Again, that's not always feasible. And I'll talk about that a little bit later too, but that deals with reactivity and just seeing things, seeing the treatment and the outcome multiple times. There's a lot of extra care that has to go into those kind of designs. And additionally, you have to consider other factors to increase the validity of that kind of design. But it is a good design and one I use often. And then homogeneous participants. So I mentioned earlier that if we have, like with the blocking, we could just get a sample of people that are all very similar to one another. So there's almost, we minimize the amount of heterogeneity across individuals. However, that is probably the least recommended approach, I think, because that severely dampens your ability to generalize the results to any population other than the very specific group that you studied. So increasing power can be tricky, but it's, we want to make sure we have at least enough power to detect effects for our primary goals. And if we don't, that can actually undermine our ability to detect a causal association. So another thing we need to consider is whether the assumptions of the statistical test that we use have been violated or met. So violations of the test assumptions can lead to either overestimating or underestimating the size and significance of the covariation that you find. So you could just think of if you have a just 2 variables that are correlated and you have an extreme outlier. That extreme outlier, depending on where it is, may or may not have an effect on the results, but it's possible that it makes the correlation look way stronger or weaker than it would, or even flip the sign. So this is my little pitch to make sure that everybody always, visualize your data, plot your data. That's the first line, one of the first lines of defense. Look at all your descriptives and then plot the data. That's one thing to look at. You could also use different kinds of estimators that are more robust to violations of assumptions that have been developed in more recent years. But the other thing, after you visualize your data, you should evaluate the assumptions of the statistical model that you're using, and then also understand how robust the model you're using is to violations of those assumptions. So for instance, with a t-test, if the sample size is large enough, violations of normality of the residuals are not that impactful. However, if you have residuals, the variance of the residuals are not equal across all levels of your predictor. That's what's called homoscedasticity. Or in ANOVA terms, it's homogeneity of variance. So I think that's the easier way to think about it. If all 3 groups have the same variance, you're fine. If they don't, they may come from a different population. They may bias your results. And we have new estimators, like sandwich estimators and things that can actually account for violations in that. So things that used to be more difficult to deal with or resulted in us having to do either just settling for a violation that yielded unbiased or biased results or doing transformations to the data that made things more murky. We don't necessarily have to do all that anymore. Um, so another thing that we have to consider, and this is related to power as well, and also to the so-called replication crisis in the psych and social and behavioral sciences, is phishing and error rate problem. So phishing is um, more of a metaphor, but it's just going into your data and just trying to find what's significant and then reporting those results and then not reporting the results that weren't significant. I think that's kind of the crucial part there is omitting non-significant results. And people don't necessarily do that for nefarious purposes. There's a lot of just historical context of, people being trained to do that for a long time. And also journals just only wanting to see significant results kind of encourages that. Um, But when you do that, if you don't correct for all those extra tests that you do, you don't have the alpha level that you thought you did. So every extra test that you do increases your alpha level. So you may set it to 0.05 and say, look at these 10 tests that I did. Or let's use the example I have on here. Look at these 3 tests that I did. With alpha level 0.05, they're statistically significant, all 3 of them. But your alpha level actually inflates each time that you do a test. So in the case of 3, you would have a 0.143 alpha. So no longer you're working at a 0.05. You think you are, because each individual test, that's what you're comparing your p-value to. But now it's actually 0.143. So you actually need a stricter alpha level. You need to lower it down because you may set it at 0.05, but it's actually higher. So this can lead to overconfidence in your findings. But like I said, how this is related to power, there are different methods to correct for multiple comparisons. A traditional way that people used to do it was the Bonferroni correction, which is still pretty common today. However, the Bonferroni correction, that can get very unwieldy fast because you divide the alpha level. So if it's 0.05, you divide 0.05 by the number of comparisons that you're doing. So if you do like 1, or if you do like 2 or 3, you're dividing the alpha level by 2 or 3. But what if you did 10 tests or 15 tests? You all of a sudden very quickly get to an alpha level that is not feasible to detect an effect on. And if you can't detect an effect on your alpha level that's actually there, that's an issue of power. So when you correct for multiple comparisons, you are inherently reducing your power because you're basically making a stricter alpha level. So that's one thing that I want people to consider with this particular thing here, regardless if you're doing causal inference or not, when you're powering your studies, if you do plan or think that you'll do multiple comparisons, it's good to actually power for that. Because otherwise, if your study's powered exactly at like 80%, if you do multiple comparisons, it's no longer powered at that anymore because you have to work with a stricter alpha level. And there's actually a lot of debate in the literature about people correcting for alpha levels, whether you should do it and how you should do it. There's a lot of methods to do it now. Some of them are more conservative than other approaches. So it's kind of a mess, but I think in general, as long as you justify what you do, um, it becomes defensible. So I mentioned this earlier, but unreliability of measures. So this can happen when you have some kind of measurement error. And that can weaken the relation between 2 variables. And if you have more than 2 variables in your model, it becomes unpredictable what happens. Sometimes you overestimate, sometimes you underestimate, and there's no systematic kind of pattern there. And most of what we're doing is actually looking at multiple variables at once. We tend to not just look at how one variable is related to the other. And as I mentioned earlier with confounders, for instance, if we want to make a causal association, sometimes we have to control for a confounder. So right there's already three variables in the model. Um, and depending on what field you're in and the type of research you're doing, the amount of measurement error can range from very little to none to a lot. So in the psychological sciences, we may have a lot of measurement error in some of our measures, and that's why we've developed a lot of statistical methods to help control for that, like factor analysis and structural equation modeling. There are ways that we can help with reduce the influence of measurement error, though. So one is to have more items. And if you've ever looked at something like internal reliability, so like a Cronbach's alpha or a McDonald's omega, you see that when you add more items, the reliability tends to go up. And that kind of, when you have more items, the amount of measurement errors starts to wash out. And I also put raters here because if people are doing developmental research and maybe they have people observing children's behavior and coding it, having more raters can actually help. Having better quality items or more trained raters is a related thing. So just having items that reflect what you're interested in better. So if I'm looking at loneliness, I probably don't necessarily want an item that says, um, I get lost in my thoughts. I mean, maybe that's semi-related to loneliness, but an item like I feel lonely or I feel disconnected from people, um, those might be stronger indicators. So having more items like that. Same with the raters. If you have people rating different behaviors, the better trained they are, the better that they're all going to converge on the same answers and be consistent with how they judge behavior. And I think I did mention this, but the latent variable models, so that's the factor analysis or the structural equation model, those are specifically developed to ideally separate out measurement error from some kind of true score. So ideally, in those models, if they're specified correctly and the measures are still done with high quality, we can actually disentangle the parts that are measurement error, and that can actually help us with our statistical conclusion validity. So restriction of range is an interesting one because it can happen for so many different reasons. We could purposefully restrict the range of our data. We could collect data and it just happens to be restricted, or people could happen to only score at the high or low ends of the data. So restriction of range is a reduced range on the variable. So if my scale ranges from 0 to 100, but everybody's scoring between 45 and 55, when I actually do the analysis, I'm not actually looking at the whole range of that anymore. I'm only looking at a very small section. And depending on the way the data looks, that small section, say we have something that's nonlinear where it increases to maybe 40 or 50, then it flattens, and then it decreases. If I'm only looking at that small section between 45 and 55, I might say there's no relation between that variable and some other variable because that particular range that I looked at has a flat relationship. But if I look at the entire range, I might see, there's clearly some nonlinear association here, and I couldn't detect it because I squished the range of my data. So now it's become difficult to find the relationship. It's weakened it, and it could also reverse it. You could have ceiling or floor effects. So that's where people tend to score only at the highest and lowest ends of your data. And there could be multiple reasons for that to happen. There's been some statistical methodology developed in recent years to kind of help with that. One thing that is still pretty common, and I'll do it sometimes to help with interpretation, but I always include a version of the analysis where I don't do this, or try to find a better approach. But if we artificially group continuous variables into categories, that is by default restricting the range of the data. So that is where we dichotomize, trichotomize, any kind of grouping of a continuous variable into different kind of discrete categories. Because now within those discrete categories, there's variability, but we're just giving everyone the same number now. We're saying you are all in group 0. We don't care that some people are high and low in that. So we're by default restricting the range of the data that way. Interesting with that is sometimes that can make you find effects, and sometimes it can hide effects. But when it makes you find effects, they may not necessarily be real. And when people do this, they're often doing it because there's some kind of nonlinear relation between the variables, and a very straightforward kind of first pass thinking of this is to say like, oh, if I just look at mean differences between them, I can see one's high, one's low, and the other one falls in between or higher. But there are different statistical approaches we can take that will allow us to kind of look at the data, how it kind of, the wiggliness in it, I guess, without having to artificially cut these variables into groups that can actually impair our ability to make inference. Also, maybe we have a treatment and people just happen to have the same range of values. They're really narrow group. So that's not anything that anyone, purposely did. It's just we recruited people, and the people that would happen to be in this study happen to have a restricted range. And again, this is where it becomes crucial to look at your data before you start doing these things to understand if that's happening, and then if you need to go out and recruit some more people or take a different approach to your analysis. But all these can affect our ability to make a causal claim. So if we don't have a reliable treatment implementation, that can also undermine our ability to make a valid statistical inference. So if a treatment that is intended to be implemented like the same way across all people is only implemented that way for some people, then our ability to detect the effects going to be impaired. So it could be that some people in your treatment group get a very rigid, strict, clean version of the intervention, and other people, maybe they have research associates who aren't as trained in it yet, and the way they deliver the intervention is kind of messy. Maybe they forget some things to do, or they take a longer time. That kind of variability that we have there is all going to be captured in the error that we have. So some of the people in the treatment group are going to have a weaker effect than they would have if they had gotten the fully standardized optimal version of the intervention. This can happen in a lot of different ways. So if you have a multiple site study, which, some data sets I've worked on like that are like the long scan data set, where data are collected at different sites across the United States. Or if you're doing like a cluster randomized trial where you have different sites randomized to condition rather than individuals. If there are differences across the sites in how people are actually implementing the intervention, that could affect your ability to detect effects. Luckily, my work with like long scan, I haven't run into that issue, so that's been nice. They've put a lot of effort into that standardized approach, and often this requires multiple training and retraining to make sure people are still doing things the way that they're supposed to across all sites and across time. Speaking of across time, sometimes people like raters of children's behavior get better as time goes because they have more experience with it. So as the study progresses, they get more accurate in the way that they are categorizing behaviors or describing them. And then that means things that were categorized earlier are going to be less reliable than things that are categorized later. So when you're looking at group differences and comparisons, you're also going to have that extra amount of heterogeneity present, which is going to essentially reduce your power because it's adding more error. Although I want to note that sometimes lack of standardization is what's desired. So this is a problem when it's something you didn't want to happen. So for instance, sometimes you want to tailor a treatment to specific individuals coming in based on their needs. So maybe there's some kind of intervention for the early Head Start program, but you provide additional resources depending on the individual needs of the participants. And if that's the case, then that is what you want to happen. And then you just consider that in your analytic approach. There may be some kind of other variables that you control for or include in your analysis in some way that accounts for that. So I just wanted to make sure that I noted that that's not inherently a bad thing. It's just if it's unintended, it can have consequences. And if it is intended, then you just have to account for it in the model. Extraneous variance in the experimental setting. So sometimes features of the experimental setting may inflate error. So if you've ever done a laboratory experiment and the temperature goes out one day and it gets really hot in the room, that can actually affect how people respond to answers. Or if you're doing an experiment somewhere and there happens, well, anyone that's on University Park campus right now, and if you're near like the nursing building, for instance, there's a lot of construction going on, but throughout campus. So if you're doing an experimental study that happens to be by a window when a lot of construction is going on for some of the participants, but not for other participants, that can actually add extra variance that makes it more difficult to detect an association and possibly reduce the magnitude of a variable. So in laboratory studies, though, you can often directly control this. Usually when it happens, it's kind of a fluke thing that's happening, and you usually note that. If it only happens to like one person, you do the thing where you do the analysis with and without them to see if it affects everything or affects your results. In observational work, though, so the work I do in ecological momentary assessment and measuring people in their daily life, there's things happening all the time. So what I have to do in those kinds of studies and what researchers in that field have to consider is think of all the potential things that could be going on in their environment. So we often ask, like, did a stressful thing happen? Did you have a positive or negative social interaction with someone? Did you stop to eat? Were you at home all day? How were you feeling? All these different kinds of variables and environmental factors that we want to measure. So I guess a good example of that is when I'm studying ambulatory blood pressure. So measuring people's blood pressure in their daily life. If I don't ask if they're standing or sitting, that's going to add a bunch of extra variability. So I need to ask about those behaviors so I can control for them, and it cleans up the analysis, doesn't reduce my power. But anytime you're doing observational work, you have to think more thoroughly about the subjects that you're studying and the environment that they're in to consider the different things you may need to measure. So for in New York City, we may need to consider noise differently than if we're in a smaller town. So I'm going to do this slide and the next slide, and then we'll take a break because I need water. Okay. Another issue that can occur is what's called homogeneity of units. And units is another word for like participants if you're doing human subjects research. It could be animals if you're doing animal research. So increased variability in the outcome variable within conditions will increase your error variance. So that makes it very difficult to detect an effect because, like I said, we're trying to find the signal in the noise. The error variance is noise. So anytime we increase the noise, there's more that we have to look through, and it becomes more like a fuzzy image. So too much error variance, it's just completely fuzzy, and we can't actually see what's going on. So this can just be individual differences in people and people that just happen to differ in these variables just based on their own characteristics. So, one way to do this is to directly measure and model these with interactions. So if we don't directly measure them, those interactions for different characteristics become part of the error. What the good news is, because that becomes part of the error, and those are things that are measurable potentially. If we measure them, then we can remove that part from the error, and it becomes much easier to detect the association. I think I mentioned this earlier. If you just collect a very homogeneous sample of people, um, that gets around this, but you lose a lot of generalizability. So if you're only interested in that very specific population, that's great. But if you're not and you're trying to make inferences to a larger group of people and a more diverse group of people, then you may not want to do something like that. When you have the larger sample sizes, then you can use the moderators. If your sample size is too small, then anytime you use an interaction term to look at moderation, you're multiplying the two variables together and you're splitting the data into smaller parts. So you do need a larger sample size often to do that. And if you use a within-person subjects design, in those designs, participants are actually compared to themselves. So it'll depend on the correlation between the pre and the post-test measure, but those can often help with this homogeneity of problems. So it's one thing we do a lot in the ecological momentary assessment world is when we create a variable that only changes within individuals, they're inherently just compared to themselves. So that actually helps with a lot of the between person kind of variables that can impact our results. And the last slide before we take a break is inaccurate effect size estimation. So some statistical methods can over and underestimate the effect size in a systematic way. So I mentioned this earlier, but if you have an outlier that can actually decrease or increase the effect size, it depends on where it is in the line of the data, how much influence it has. Sometimes it can make the slope look bigger, but it adds more error. So it actually, the effect size goes down. And I'm going to say something that I see a lot of debate about on like Blue Sky and Twitter back in the day. If you use like a linear model that requires a nonlinear model, that can cause issues. So if you're looking at a dichotomous outcome and you use a normal linear regression, the standardized effect size that you get from that is meant for continuous variables, normally distributed continuous variables. And that will actually give you a biased effect size estimate. So in those cases, it's typically better a measure of effect size to use an odds ratio. But yeah, that's a contentious topic because there are linear probability models and other factors that can be, it depends on what your purpose is. But ultimately, it's use the correct statistical method for the data that you have, the relations among variables that you're trying to model, and the question that you're trying to answer. Yeah, so I think this is a good time for a break.
All right, John, when do you want people to come back, or do you want to let them ask questions if they have from the first section? Oh, actually, there is one person, Nathaniel has raised his hand, so.
Yes, I've been following the presentation and I think this might be a good time to ask questions because I actually I know a lot about effect size issues and I actually did a power analysis using a for logistic regression analysis, which uses the mean instead of the odds ratio instead of the means. And I actually had a paper that had a power analysis, and they said I had to use a mean. So I agree with that, and I because that the effect size issue for something that uses an odds ratio is more appropriate for binary variables, whereas the mean base is more for continuous, but there's still people who just insist upon the mean base analysis. And
Yes.
two, I wanted to mention about an issue that I've just been dealing with a lot in my research that you don't really discuss in much detail how to deal with missing data appropriately because the default manner of simply excluding them without understanding them is a decrease of sample size, and all data is important. And I've just been reading some studies on that if you don't do any analysis of knowing if it's random or not at random, then it could bias the whole study. And that's an issue that is very important in any analysis, is making sure that the missing data is handled appropriately. Because, for example, and I'll give you an example. I do a lot of peer reviews. I actually did a review. It was a study in Philadelphia, and they had like, and I asked because they had like 30% missing data in their analysis, and I actually rejected it because and I and this is why, because they just simply excluded it without knowing if it was random or not, or random. And that's a big problem, to have 30% missing data and not account for it, because that is, because if you do power analysis and all that, and it's missing data, that decreases the power analysis as well. And it could actually affect the external validity, not accounting for the missing data and things like that. And the fact that there was no mention of that issue, it's just concerning.
So that's a really good point, and I do have stuff on missing data coming up. I have it put into the internal validity slides, which will be what I'm coming up with. But I agree, it is a problem that is part of all aspects of validity realistically. So it does affect external validity because now you're generalizing to only the people that completed the study. It does impact statistical conclusion validity because your statistical methods now are based on a different sample than you thought, and you may be making inferences beyond what you can. But also the internal validity. So the type of people that would be missing, why those people are missing, and the people that remained in the study. So there's a lot of work on a different kind of causal estimates, which is not something I want to go
Yes,
over
yes,
today.
yes. And to give you an example of how missing data can be useful, I did an HIV study, and a part of the HIV study is an unmet needs analysis, which is actually using the missing data to try to understand where the unmet needs are. Because if there is, so simply excluding the unmet needs, and because it just depends on the research question, that it's more for quality improvement, not so much on research. But and that's another issue I wanted to bring about. The NIRBs, it just simply focuses on the research definition, and there's actually a big issue of non-research, which is like quality improvement, which is underused but still important. If it because And I know that the study designed for that quality improvements are vastly underrated, but because for quality issues, it is important to analyze where the missing data came from and to understand, and for unmet needs analysis, not so much for the research question, but for quality improvement. And I just wanted to bring that up now, that just because and that's more tributary or secondary analysis, and that is part of the reason why I tend to do more secondary or tributary analysis and not so much primary data analysis, just to handle issues like that.
Yeah, that's a very good point. Thanks for bringing that up, Nathaniel. That it is crucial for the missing data, and I'll go over that a little bit in the slides. But anyone really interested in diving into missing data, I encourage you to look at work from like Craig Enders and also Seamin Chow, who's a quant dev faculty in human development family studies. Done a lot of great work on that. And a lot of the work that I do with ecological momentary assessment, missing data has traditionally been handled as just, slap the word full information, maximum likelihood, or FIML on it. So there is some work now coming out trying to figure out how we deal with missing data better and not just assume it's missing completely at random. And some of the other work I've done, even in causal inference, has looked at handling missing data. Um, uh, I'll talk a little bit about this study later on, but I used something called a synthetic control method, and we had a lot of missing data, and we ended up using multiple imputation because we found several factors that were measured in the data set that were related to whether someone was missing or not. And that provided us some evidence that data were missing at random. But the issues come in when data is missing not at random. And that's when it could really bias your results. But regardless, just doing a complete case analysis where you remove people missing and just ignore them. If your data is missing completely at random, truly, there's no reason, it's just happened, you're still reducing your power, but it's unlikely that the data are going to be missing completely at random. So you're going to have issues with power and also issues with the validity of your causal effect and the statistical conclusions that you make.
Yes, I agree with everything. Another issue I wanted to bring about that I actually dealt with on my analysis that I requested $10,000. I had 10,000 cases for secondary data analysis and on New Jersey, and I actually got a data set from the New Jersey Department of Health, state-specific BFRSS, at $14,000. So I actually had an overpowered sample, and there was no issue with doing the analysis per se, but with IRB issues, I didn't know this at the time because I only put on the request 10,000 cases and I wanted to close the IRB application. I actually didn't know this at the time, but because I had a larger sample, I actually had to do a modification of the IRB approval and on that issue by itself, and then in order to close down that study. So I know there's underpower issues, but there's also another extreme called overpowered, and I guess that I didn't realize at the time that is worth mentioning as well.
That's a very good point. Part of that too is just resources and the burden on participants. So that's why the power analyses are important, and also to consider in the longitudinal study how much attrition you expect and account for that in your power. But yeah, you don't want to recruit too many people because at some point you're not getting any more return on the power. You're just you have the effect well estimated, and you're just adding more people who don't necessarily need to be in the study. So wasting resources like money, but also the participants' time, and depending on what the study is, any discomfort from it.
That actually does make sense, and I don't want to interject anymore, but sometimes if you have missing data, for example, you need the extra cases to account for the missing data. So how do you balance the issue of accounting for missing data and actually having something overpowered? And that's another question.
Yeah, so for me, for instance, if I needed 100 people to power my study, like if I was doing a growth model to look at how people change over time, and I knew there'd be 20% missing typically based on previous experience with research, but also what's reported in the literature, I would then recruit 20% more. And then expecting that 20% will drop. So hopefully, if I expect 20 people to drop, I'll recruit 120. And if those 120 drop, I still have my 100. And then I just have to then be cautious and mindful with what I do about the missingness in that.
All right, sounds good. Thanks, Nathaniel, for the interesting discussion points that you brought up. So, yeah, John, so I guess we can take a break. When do you want people to be there again?
I mean, I guess we can come back at does like 5 or 10 minutes
10
sound?
minutes, maybe?
10 minutes, yeah.
All right,
Well,
yep, take a
so
break of 10 minutes and then
probably
don't,
3:20.
I won't, let's not quit the Zoom room so that people are still there. But we can resume at, let's say, 3 20. I mean, it's 12 minutes, but yeah.
Sure.
All right.
Works
Okay.
for me. Thank you.
All right. Thanks, John. All right, I think we can restart, Johnny.
Okay. Sounds great. Okay, well, welcome back everyone that left for a moment. And if you're not back yet, you'll jump in when I'm in the middle. Can you still see my screen? Perfect. All right. So, before the break, we talked about statistical conclusion validity, which is our confidence that the statistical methods we used are the correct ones, essentially. Are we getting the correct statistical covariation among variables? But we still don't know from there how what we are observing, whether it's a causal relationship or not. So internal validity, as defined in Shadish, Cook, and Campbell, is inferences about whether an observed covariation between two variables actually reflects a causal relation. And specifically in the direction the variables were manipulated. So if I manipulated, somehow was able to manipulate whether someone had smoked their whole life or not, and it was related to cancer, I wouldn't say that cancer caused smoking because the manipulation was on the smoking. So in that case, you would say smoking caused cancer. And as a reminder from what we talked about above from Stuart Mills, so in order to establish causation, you must show that one variable came before the other, that the two variables are related, and that no other plausible alternative explanation of the observed covariation exist. And that's really what is going to be the crux of this internal validity discussion, is that last point, although the other 2 points are important and still part of it. So, if internal validity is the evidence that we have for a causal effect, or the strength of belief and support that we have for a causal inference, we need to know what the threats to that are. So these are a list of some of the threats that are gone over by Shadish, Cook, and Campbell. And these I feel like are some of the most important things to consider when, especially when designing a study. So even if you're not necessarily thinking of causality, your research question is probably causal. They tend to be. You can see if looking at any of these factors, if there's anything you could include in your study that could help rule out some of these, because even if you can't make a strong, like I'm confident that this is a causal claim, maybe you provide some evidence, and then I can kind of build across different papers. So I'll talk about all these kind of one by one, like I did before statistical conclusion validity. So the first is ambiguous temporal precedence. So again, this just goes into the cause has to happen before the effect. We need to be able to know that one thing happened, a change in it occurred, which then led to something else happening later. And that timing and later is completely dependent upon the research question, the variables used, the subjects under study. And it can be completely different even within, if we're just studying people, some things change over decades, some things change moment to moment. So lack of clarity about which variable occurred first can give you confusion about which variable is the cause and which one is the effect. This is particularly true in correlational studies. So when we do like a randomized experiment, we know which one happened first because we made the manipulation. We assigned people to conditions and then measured what happened because of that. So in correlation studies, though, sometimes a direction can only go one way. There's no other way that it could happen. So, with the like smoking and cancer study, someone who smoked their whole life and then got cancer, it probably goes that direction. Cancer doesn't necessarily cause smoking. And these are things that we can really start seeing in longitudinal studies. So when we have longitudinal correlational studies, sometimes we can get some evidence for directionality. And I'll talk a little bit about that, something called Granger causality. It's not quite a sufficient condition for cause because something else can be explaining why two variables are related over time and even temporarily, but it is one thing that can help us get some evidence and then maybe look at other factors that can rule it out. So random assignment to conditions does produce directionality of cause and effect. So there's a lot of reasons that people prefer randomization when doing experimental designs, but it's not the only way. It's not always the best way, depending on what you're studying. So the fact that A happens before B or some variable happens before another is not enough to say that it causes it, right? So we could have reciprocal causation. For instance, criminal behavior could lead to prison time, but more prison time could then result in more criminal behavior later, which then results into more prison time. So it's not clear the directionality on that relation. It goes both ways. With time series data, though, we can actually test bidirectional lagged associations. And, I've done this in some studies where we use something called like a random intercept cross-lag panel model, or some kind of Bayesian multivariate model where I can model multiple directions, lagged associations, and multiple dependent variables at the same time. And when you include both directions in the model and the contemporaneous or the relationships that happen at the same time, you can actually get a cleaner test of whether something is consistently going in one direction or not. You can even get tests depending on the sample size and the amount of time points, even maybe over development when a relationship goes one direction, if it starts changing at a different age. But anyway, this is something that would be called Granger causality. But it's not true causality, right? We can't establish that one variable happens before the other, but remember there are two other things that need to be considered to have a causal claim. So just because something happens close in proximity and before something else and is reliably related, there could be other factors that explain that relationship that need to be ruled out first. So one of the biggest issues that can occur in experimental design and is a big threat to internal validity is what's called selection, which can cause selection bias. So those are differences over conditions in the respondents, participants, subjects under study that could actually cause the observed effect. So for instance, if we had like an educational intervention and the intervention part was only given to children whose parents volunteered them, and the control condition was just all other children who didn't volunteer in the study, and they just consented to having their test grades collected. Well, the volunteering parents may also do other behaviors, like they're already going out of their way to help their kid get some extra assistance in their educational adventure. So maybe those parents are also more likely to read to their children than parents who didn't volunteer, or maybe they're more likely to have other kinds of resources available to them. Those are the type of factors that could actually affect the outcome, because then it's not just the intervention, but it's the intervention and the types of people who would go into that intervention because they selected it. So you have a confounding of treatment effects with population differences. And there are ways to try to unconfound that. Some kinds of moderation can help, but that becomes tricky. If we truly randomize people into conditions, that's here, yeah. If we randomize people to conditions and we do the randomization correctly, in the long run, random assignment to conditions eliminates selection effects, because we now know the method that people got into condition was because we gave them, say, a 50-50 probability of being in one or the other. So selection is purely random, and we no longer have to worry about the other threats that selection can bring up. In a quasi-experimental study or an observational design, you actually need to collect variables that may produce a meaningful difference between individuals in each condition that's also related to the outcome. So there are a lot of different approaches to go about handling selection after you've collected the data. One of the more common ones is propensity score matching or propensity score weighting. Those were developed explicitly for this. And those basically you take those variables that you collected that explain why people are in different groups, and you use them as a predictor in a logistic regression to see how they predict the likelihood that you're in the control versus the exposure condition. And then you can get weights from that represent the propensity of someone being in one group or the other, and include that in your analysis. And if you have collected the correct variables, all the variables for that explain the selection, then you can actually get a valid causal inference from that. But from work I've done with these, it is challenging to work with this, especially in secondary data where the intention may not have been to do this, so all the variables may not have been collected that you need. But again, we're trying to provide as much evidence that we can for the causal association, so sometimes we can get close. We also have things called history effects. So history are events that occur at the same time as treatment that could also cause the effect. So if we're doing like a study on the effects of WIC programs, so the women, infants, and children, that we want to use to improve pregnancy outcomes in eligible low-income women compared to non-eligible women. So one of the issues with this is if you qualify for WIC, you may also qualify for federal food stamps. So if we're doing an intervention and we're comparing people on WIC and people who don't qualify for WIC, people who don't qualify for WIC may also not qualify for the federal food stamps. So that could explain observed differences, because the difference you're seeing may be because one group has fewer resources or the other group is just getting more assistance already. So it may not necessarily be the manipulation that you did, but it's something else that's happening alongside the study. So it's a history effect. Related to history in the temporal sense is maturation. So these are naturally occurring changes over time that can be confused for treatment effects. And as I say this out loud, this sounds similar to something called regression to the mean, which I'm going to talk about in a little bit. But in maturation, participants naturally can change during the study. This is particularly true for very longitudinal studies, but so people can grow older. They can get hungry, they can get fatigued. So, we've done studies, previous work I've done with large cognitive batteries, and some of those can take a very long time to get through all of them. And we flip the order of when tests get taken by different participants to help kind of mitigate the effect of fatigue on any one specific test. But typically people get worse performance over time on a long cognitive battery. And another example is if the local economy is growing, then employment rates may increase regardless of an intervention that was developed to increase employment rates. So that's just the at a city or town or county level maturation. But you could reduce the impact of maturation by recruiting people of similar ages from same locations. That's creating a slightly more homogeneous population then. So you do have to adjust who you are generalizing your results to. So I've had some studies that I've worked on that have done this, where we looked at child maltreatment, recruited people from ages 6 to 16 and followed them for 35, 40 years. So the study started when I was a baby, but they recruited people from a community who had experienced child maltreatment, and it was substantiated by Child Protective Services. And then they recruited a group of people from the same communities in the same age range with similar other demographic and other psychosocial factors, so that we had some kind of evidence that these are people that are, as close to similar as possible, with the primary difference just being whether they had substantiated child maltreatment or not. And then we can follow them over time to see if there are any differences and have a little bit more confidence that it's not just maturation changes, it's not just history, because these are people in the same area. and over time. And what I mentioned before with regression to the mean, so this is, most often happens when you select people based on extreme scores. So maybe you pick people who have the highest levels of depression and bring them into your study. Well, if you do that, they're more likely to have less extreme scores on other variables because you're selecting them to be extreme. And they may be more extreme than they typically are, so they're going to come back down. This can easily be confused with the treatment effect. There's actually recently some discussion about placebo control studies, and sometimes you actually need an extra condition in those because just comparing to a placebo alone, sometimes that could be regression to the mean. So you have another condition without anything going on, and then you could really pick apart regression to the mean in there and disentangle that from your results. But some examples are a person that scores the highest on their first math test probably isn't going to score the highest on their second one. They're going to score high still, but probably not the highest. A person who goes to therapy who is extremely distressed, they'll likely have less distress on later sessions, regardless if therapy was effective or not, because they came in when they were at the most distress that they've had. And you tend to, with regression to the mean, you tend to become less extreme over time. So it becomes difficult to determine whether that was due to just time or the therapy. So this is a threat whenever subjects are selected because they had scores that were higher or lower on average. And there are ways to go about addressing this, but it typically occurs because measures are not perfectly correlated with one another and have over time and have random measurement error. So interestingly, quantitative analysis is not required for regression to the mean to occur. So it's not regression in the statistical model sense, it's regression and we're going back to our baseline level, to a less extreme version. There are a lot of methods that were developed to kind of go over this, but if you create a large pool of people with extreme scores, you can actually randomize within that group, and then that will be able to unconfound regression to the mean and receipt of treatment. There's other statistical methods too that kind of help with this, like regression discontinuity designs, because people tend to be assigned based on a value of some continuous measure, and those designs can have some nice little tricks that allow you to get a valid causal inference, assuming all other threats to validity are also addressed. And now we'll talk about attrition. So this one's for you, Nathaniel. But we talked about that a little bit before break. So I'll go a little bit faster on it now. But attrition, also known as mortality, depending on the type of research that you're doing and the tradition that you come from. But it's loss of respondents to treatment or to measurement. And it can produce artifactual effects if the loss is systematically correlated with conditions. So basically, if different kinds of people remain in one condition than the other, those differences can explain the post-test outcome. So why people differ. What that causal or that covariation that you find could be due to the type of people that stay. And if that sounds familiar, it's because that's a special case of selection bias. The type of people that remain in the study are different than the type of people who dropped out of the study if you have some kind of systematic differential attrition between groups. And as we mentioned, if samples, if you do have missing completely at random anyways, the loss of people will reduce your power. And that could also affect your ability to detect an effect and maybe reduction in the magnitude of the effect. So, just a quick example. If you're comparing the GPA of college students when they were freshmen versus when they're seniors, you may find that the seniors have higher GPAs than the freshmen, but that could just be because only a subset of the students made it to senior year. So not everyone that started as a freshman ended up being a senior. So a higher average GPA could just be that the students who had the worst GPA ended up dropping out. So that will automatically, you're removing people who are in the lower end. That's going to artificially increase your mean just based on that. So from attrition, you can get an association that's not actually real causal effect. It could be confused for it. So this is one of the reasons that paying attention to missing data is crucial, not just in causal inference, but in valid statistical inference as well. We have things called testing effects. So exposure to a test can affect scores on subsequent exposures to that test. And that could be confused with treatment. So maybe you take the same math test over and over again, and you have an intervention in between to help you improve on the math. Well, if you're taking the same test, you can just be learning how to respond to that test. So you improving on the test may be because you've seen it multiple times. But this, it depends on what you're measuring, right? So if we measure someone's weight, maybe that encourages them to gain or lose weight because they see what's on the scale and they're like, oh, I want to change that. But if you're measuring someone's height, that's unlikely to result in a change in height. So testing doesn't necessarily affect all instances equally. It's more of an issue when tests are completed close in time and the same form is used. If the tests are a long time apart, then there's going to be some forgetting that happens and that influence will be less. But I will note that this is actually something we do a lot in the Center for Healthy Aging because we have people take mobile cognitive assessments multiple times a day for multiple days. And we address what's called the learning effect. So just over time, they get used to the test, and then we can actually finally find their ability, their true ability on the test. We see a nice kind of curve, but we have recently found that that curve is kind of maybe important. There's individual differences in people's learning rates that we do a lot of stuff like that in the center. So sometimes that testing is actually something we can leverage. It just depends on the context of the study. Instrumentation is about how the nature of the measure can change over time or across conditions. So one thing, because I do a lot of psychometric stuff, I do work with measurement invariance. And measurement invariance is just about, does the measure reflect the same thing in multiple groups of people, and does it reflect the same construct over time? So this is a related issue. However, there's some other issues that can come up with instrumentation effects. And if you don't address them, they could be something that look like the treatment effect. So you do need to rule that out. So observers of human behavior become more experienced and report more accurate scores as the study continues. So I kind of touched on that earlier, but if they're becoming more accurate, then that is changing, and they actually may look like the participants are improving when they're just being measured better. When you study children as they develop, the type of measures that you use sometimes have to change. So we've run into this while looking at depression in the same group of people who were exposed to child maltreatment. We had a children's depression inventory and then an adult depression inventory when they got old enough, but those aren't necessarily directly comparable. So when you do have like a measure that changes, one of the things you want to consider is including items from the previous measure, because that allows you to do some extra things like calibrating to see the equivalence of the two measures. And this isn't just with people. So if you're studying like animals, let's say you have a rat that needs to suppress a bar, and the bar has a spring loaded, but over time the spring becomes weak, or it becomes weaker and weaker, and the bar ends up being pushed down faster. So it looks like the reaction time is increasing, but it's actually not the reaction time that's increasing. It's the instrument is needing to be updated. So some takeaways I wanted everyone to have for causal inference and validity is the approach here going forward is that causal inference is more of a qualitative judgment rather than a quantitative value. So there are statistical methods that have been developed and that like I'll use often to help address some threats of internal validity, but ultimately the design of your study is what's going to help you determine whether a causal inference is valid or how valid it is and what threats exist to that causal inference that are actually plausible. Yeah, so that's kind of the main general takeaway for this whole validity kind of discussion that we just had. And I have some more stuff, especially resulting in DAGs. But I do want to encourage people that when they're designing studies to consider causal inference in the variables collected. I know we have limited resources and time, and we can't just bombard our subjects and our participants, whether human, animal, anything, with too much. But if we could include one or two things that address each of those threats, that can really help us move the field towards looking more at causal inference. I just want to touch on some of the different designs that we can use to address these threats to internal validity. Randomized experiments is typically something that is often touted as the gold standard. And there's a reason that people talk about that. Because when it's possible and when it's done correctly, randomly assigning participants to conditions can rule out many of the threats to internal validity. So randomizing to groups in the long run. So when I say in the long run, it doesn't mean that in any specific instance of a study, randomization will ensure that your sample has, good balance between confounders. It means in the long run it will. So over multiple studies. And that's where you get into like a meta-analysis of 20 randomized experiments. In the long run on all those, the confounders will be evenly balanced, so you can get a good estimate from a meta-analytic mean, for instance. But yeah, it ensures pretest differences are equally distributed across groups. That's crucial for selection, for instance. Like we don't have to worry about those factors. Temporal structure is imposed, so we know because we manipulated our variable and then we measured the outcome, so we know the directionality. We have temporal asymmetry. X happened before B. Other threats could be evenly distributed across groups, so they become less plausible alternative explanations. And there are different study designs you can do to help too. If you measure multiple pre-tests and multiple post-tests before the manipulation occurs, that also helps you just measure things like maturation and other things that occur over time, like history effects. That's just what I was just talking about here. So there's a basic randomized design where you just randomize people to two conditions and then measure their outcome. But we could have a pre-test, post-test design where we measure people before the intervention and after in the control and the treatment group. And then we compare how their change in pre and post-test scores differs between groups. This kind of approach is known as the difference in differences. We have factorial designs, so that's where we talk about the blocking and the moderators. So sometimes we have an intervention and then we look at how the intervention is different across men and women, because now we've created two groups that are more homogeneous than the overall sample would have been. So it can increase power, but could also allow us to determine if associations differ across people. Longitudinal designs, so the multiple pre-test and post-test. But I think the randomized experiments are a little bit more straightforward, although they're not always the correct approach to use. So my work in child maltreatment, for instance, we can't randomize people into those conditions. It's not ethical. But we still need to make causal claims, and that's important. It helps us develop interventions. This is like we've done with smoking and cancer, for instance. So Ed Diener published a really nice paper in 2022. Came out, I think, right after his passing, but it has a really great overview of the limitations of randomized experiments and also a call for people to do more types of non-randomized studies and quasi-experiments, and then utility of those kind of designs, especially in the psychological sciences, but in general. But quasi-experiments, and non-randomized designs are still experiments. They have the same purpose as randomized designs. We just need alternative approaches to address the threats to internal validity because we can't rely on random assignment to help us kind of rule out those. So when doing a quasi-experimental design, and that is just a design where we have, so for instance, when I look at child maltreatment, differences, I'm looking at people with child maltreatment and people without, but I didn't randomize them to those groups, but it's still an experiment because I'm looking at the difference between them. So that's a quasi-experimental design. But in this, you have to identify and study all the plausible threats to internal validity. So note that in some of your studies, some of those threats won't be relevant, so they won't be plausible. And there's lots of different threats within each, or factors within each threat, and not all of them are going to be relevant to your specific study. So you only want to look at the ones that are plausible, that could actually, you have some evidence for, and then account for that. Primacy of control by design. So you want to have control groups and pre and post test assessments. And then there's coherent pattern matching, which is an approach I particularly like. So basically what this is doing is if you can't do the random assignment and you're having trouble maybe collecting variables to rule out threats to validity, one approach is it's almost like a triangulation of the effects. So I know that based on my theory, child maltreatment should be affecting internalizing behavior disorders. So I make that prediction and I find that, and it increases it. Then I say, okay, it should also increase externalizing behaviors. And I find that that's true. And then I can find another variable that it shouldn't be related to, or that it should be negatively related to and decrease. So maybe I also predict that child maltreatment decreases cognitive ability, which is something I've found in a paper recently. And now I've made multiple complicated predictions that are all coming out the way that I would expect. That gives you more confidence that you've found a causal relation because it's not just one relationship. You're now making a hypotheses about a whole complex set of things that you would expect to find. There are a lot of different types of quasi-experimental designs, and I'm only talking about a few of them here. These are particularly good designs to help rule out many threats to internal validity. So you could have what's called an untreated control group with pre and post test. So another name for that is a non-equivalent comparison group design. So that study that I did with child maltreatment is a untreated control group or non-equivalent comparison because they're totally different people. They weren't randomized to it, but I did put a lot of work, or not me, the people who ran that study in the 80s put a lot of effort into making sure that these people differed as little as possible, but it's still a non-equivalent comparison, and we're following them over time. The only problem here is we don't have any pre-tests, so it's only a post-test one. But in an ideal world, you have many measurements beforehand and many measurements after. And if we could show that they don't look any different before the intervention occurs and they only look different afterwards, then we have more evidence that the intervention was actually what caused the difference post-test, especially if the intervention pre-test looks the same. And I'll show an example on the next slide of what I mean by that with a type of interrupted time series. An untreated control group with switching replications. So maybe you get people before they had the treatment, and you get some people that already have it. And the people before they get the treatment, you have some kind of run-in period. So you can actually look at what happens when certain groups of people don't get it until a certain time point. And then interrupted time series, in particularly when you have a non-equivalent control group and a non-equivalent dependent variable. So what this would mean is you follow people over time. It could be over days, years, months, and you have measures before and after an intervention, and you have a control group over that same time period who didn't receive the intervention. And you have another outcome variable that isn't expected to change. And this is where you're now getting into, we're looking at whether the two groups are the same before the intervention period. And if the only difference is afterwards, then we have some confidence that the intervention is what caused the difference. But if we have another outcome variable that shouldn't change, or another one that should change, that's totally different from our main focal dependent variable, we have more evidence of the intervention's effect because it's related to what it's causing changes and what it should cause changes to, and it's not affecting things it shouldn't affect. So this is just a plot that I wanted to show from a paper I recently had out in JAMA Pediatrics, where we looked at an intervention for at a county level for child sexual abuse. And you see here, we have multiple time points before the intervention, which occurred at this time here in 2017. And then we have multiple time points afterwards. And this was using a method called the synthetic control method. So it accounted for selection and other effects, history and maturation, by weighting the two groups before the intervention period. So we see that before the intervention, the groups are changing at the same, roughly the same. But once the intervention happens, we see a huge spike in the control groups, and we see the intervention groups are decreasing. So this is an example of, having measures pre and post multiple times and having a group that received an intervention and a group that didn't, where neither of them were randomized. We also collected another outcome that should be affected by this, and we see a similar trend in the plot. So that provided us a stronger rationale for the causal effect that we thought existed. Okay, so I don't have a lot of time, but I was going to briefly touch on directed acyclic graphs, or DAGs. This is something that I use in conjunction with the Shadish, Cook, and Campbell, and it's really a way to help me visualize what I'm doing. I'll just go through this quickly, but DAGs are a type of graphical causal model that had been made really popular by the computer scientist Judea Pearl. They're really invaluable for designing studies and knowing which variables to include in your statistical models. So what should you control for? What kind of analysis could you consider based on the variables that you think are in your causal model? It's important to note, though, that a DAG isn't an analysis. It's a graphical representation of what you believe the data generating process is. So I think what caused the variables to exist come from something in the population that looks like this causal graph. And I'll show an example of what one looks like. But it's important in these, the cause flows in one direction, but it can include a chain of causal events, which gets into things like mediation and other things. And it explains causation in terms of counterfactuals, which fits really well with the Shadish, Cook, and Campbell approach. This is why I kind of use these in conjunction. So just to note, DAGs look very similar to path diagrams if anyone's done structural equation models, but they are non-parametric and they're used to represent a causal association more, not analytically. So the actual analytic approach used later is not focal. DAGs are actually what's called non-parametric. So you're really just, the relationship between the variables could be any sort of shape and type. That's not really the focus on those. Some of the basic terminology. People tend to use words like nodes and edges. So nodes are just another word for variables, and edges are really the lines going, or the arrows going from one variable to the other. We can get a direct causal effect, and that's just between two variables only. You could have a mediated causal effect, where a causal association goes from one variable to another through a third variable. Confounders, we talked about earlier, those are a third variable that explains the relation between the two variables so they explain it not in the way that a mediator explains it, but they're the reason that association exists. And we need to control for that. And then there's also a thing called a collider. So that's a third variable that's caused by the exposure and the outcome. So I'll show some pictures of what that looks like and what to consider with those. So a direct causal effect is where X is related to Y. A mediated causal effect is X, causes M, the mediator, and the mediator causes the outcome. A confounder, mathematically it's going to look similar in the model, but conceptually it's important is the confounder causes X and causes Y. So if you may have X and Y are related, but only because of the confounder. So if you include the confounder, you see that that relationship's not there anymore. And there's also a collider, which is represented by this U, and this is where the predictor and the outcome both cause the collider. So if you include the collider, it may induce a relationship between X and Y that shouldn't be there. So that's actually a type of covariate you don't want to include in your model. And I think importantly, this is what I wanted to show was a figure of a DAG that I drew in LaTeX. But there are multiple ways to draw DAGs. If you've done SEM, whatever program you use to draw a path diagram works. I've done nice ones in PowerPoint, and in LaTeX, if you have the patience and the know-how, it could be really nice publication-looking ones, but they could be challenging. But this is the same things that I talked about above. So here, X predicts Y through M. So the arrows go this way. This is a causal chain. This confounder here, C, causes both X and Y, which means that it could be the reason why X and Y exist. So we need to adjust for that in the model. U is often denoted for collider. X and Y are causing U. So if we include this, we actually may induce a relationship that shouldn't be there. So anything that is identified as a collider, we don't want in our statistical models. This is what I just said. I will note here, this Wysocki article is something I use often when I review manuscripts. So they talk about DAGs, and this paper is really statistical control requires causal justification. So their whole paper is about like when you're selecting covariates, you need to do it thoughtfully with the intention of causality, because that's really the purpose of including covariates is to say I'm more confident in the association that I found, which is inherently causal. But also using DAGs helps you understand whether a variable you're controlling for is a collider or a mediator. And if you control for a mediator, then you're only getting the direct effect and not the total effect, which if that's what you're interested in, that's fine. But if it's not, then you're estimating the wrong thing. So including a DAG can really help you understand what you're estimating in your models and what everything actually means. So I was going to just show everyone how to just create DAGs in R, but I think we're at the end of time. I'd be happy just to share some resources and have them emailed out. It's a pretty easy program if you're familiar with R and ggplot. There's nice code that just does that for you. Yes, so if anyone has questions, or if they want to contact me in my email or Blue Sky, I could be found at those two places. Also, I could just happy to go through the R stuff. It's not a lot, but I don't know if people need to go.
Thanks, John. So, does anyone has any questions for John?
No question here, but I just wanted to say thank you for bringing DAGs to light. As an epidemiologist, I feel like I'm always explaining what they mean, and I really appreciate it.
Thank you for saying that.
Yes, thank you. And you have references somewhere in your presentation, like for the Wysocki et al. And
Yeah, so I will send that out. Maybe I can send the slides out because I made the slides where they're all clickable.
All right, so I was going to actually say, John, if you can share the slides with me, then we can make sure that your slides are included when we send out the link to the video.
Perfect.
Thank you.
Yeah, I'll share the slides and then the R files that I made just to because the overview I did of DAGs and Dr. Fernandez Rhodes will know this is very intro. There's a lot more to it that you can do, but I wanted to give kind of the very, very basics of it.
All right. Well, thank you very much. It was a great talk.
Thank you so much for inviting me. Yeah, that was fun to be able to talk about.
I think you carried it at a really good level, so I really like the talk. So thank you very much.
I appreciate you saying that. I tried. It's the work in progress always.
It was a good talk. So, all right, thanks, John. So, share the slides with me, and I will make sure that everyone who is registered participant will receive the slides as well.
Awesome. Thank you so much.
Thank you. Thank you, everyone.